9. Several Lewis structures can be written for perbromate ion, BrO4 minus, has many Lewis structures. The central Br with all single BrO bonds, or with 1, 2, or 3 BrO double bonds. Draw Lewis structures of these possible resonance structures and use formal charges to predict which makes the greatest contribution to the resonance hybrid. Okay. So with that being said, I'm just going to say draw Lewis structures and then use formal charges to see which makes greatest, well, to see which is most stable. The reason why I say it like this is because as we were discussing with formal charges, but specifically to this question here, the formal charges, right, you want it to be as close as you can to everything being 0. That is a goal for formal charges. If there's a way, if you see like there's one that's like +1 and the other one's like -1, the goal of the, I guess, the molecule is to rearrange itself to where actually it would just be 0 throughout, instead of it having a positive end and a negative end, if it's possible to rearrange itself. That's why formal charge is help find out the stability, because you would notice that the most stable one is the one that has the least amount of, I guess, positive and negative charges. It just has the most amount of like 0 charges. So with that being said, let's draw these Lewis dot structures based on these instructions. So we have bromine, okay, and they said a single bond on each one at first. Okay, so with that being said, though, I guess a pretty good place to start would be to figure out how many electrons each is actually donating. So if you look at the periodic table, we have bromine being on the 17th column, okay, so it's going to donate 7 electrons. Oops, that's boron. Bromine is with an R. Okay, and oxygen is on the 16th column, so that means it's going to donate 6 electrons, and because there's a minus, it's going to be +1 more because electrons are negative. So it's going to be 6 times 4, because there's 4 oxygens, +7 +1. So we need to account for 38 electrons total. So 38 total. Okay. So now let's draw the oxygens. We have oxygen here, oxygen here, oxygen here, oxygen here. Okay. And now, of the 1 electron oxygen is sharing, there still needs to be 5 other ones included, because the fact that oxygen is trying to think about this, because the fact that oxygen is only sharing 1, so we label it like this: 1, 2, 3, 4, 5. In fact, I'll just say it a little differently. We start with 1 already with the sharing with the bromine, so it's 2, 3, 4, 5, 6. Same thing here: 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. And now we have that extra electron, okay, which is added here on this oxygen. So bromine, though, is only sharing so far 4 of its 7, okay? So as you notice, it's sharing 4 of its 7, but the oxygens on the outer shell all are quite incomplete, and bromine has already filled its octet rule. So being the generous person that it is actually going to just let these oxygens hold on to the other 3 left for bromine, because it's actually shared 4 of its 7. That is one resonance structure that they mention. Second resonance structure is one where bromine has one double bond, and then the third one will be two double bonds, and then the last one will be three double bonds. So the first iteration, one double bond. So we're going to signify that by just like that. Oxygen here. The rest are single bonds. And the same thing where it's 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. And the oxygen up here actually is sharing 2 already of its 6. So 3, 4, 5, 6. So I'll just move this one over here, because now this oxygen has completed its octet rule. It's all set to go. And now let's see actually if we've accounted for every electron, the 38. So just in the previous questions, I don't think I counted them. We had on each oxygen is 8, so 8, 8, 8, 8. So just to make sure, bromine, 6 times 4, yep. Oh, whoa, it's not 38. It's 7 plus 1. I don't know how I did 7 plus 7. 32. Oof, that makes more sense. So 32. Sorry about that. So in the calculator, I accidentally added another 7 instead of a 1. So we actually have 32 electrons to fill up. And as you can see here, this satisfies that. This bromine here is not quite done. Right now it's sharing 5 of its 7. So remember, we still have that one extra negative, and it's still sharing out 5 of 7. So it's generous enough to now give these other 2 oxygens a nice 2 electrons. So with that being said, let's move on now to the next bromine iteration. The next bromine iteration would be still bromine in the middle, but now it has 2 double bonds. Okay, so one here, oxygen, gonna look like the other one. This is gonna look like that one as well. Then we have these 2 oxygens that still are stingy on trying to share a bond. Oops, did too many. And as we said, there's still just one extra, and then bromine is just going to give up one of them, because right now so far it's sharing 6 of its 7, so it's just going to give that oxygen the last one. So that is going to be the third iteration. So far we're doing good. Okay, and now for the fourth iteration, we have with 3 bromine double bonds. Okay, so it's going to be bromine, double bond here, double bond here, double bond here, and one oxygen by itself. Oops, one non-double bond oxygen. And then we do the same thing, oxygen sharing 2 of its 6. So 3, 4, 5, 6. Same as the rest, 3, 4, 5, 6. 3, 4, 5, 6. And there, because it's going to be 2, 3, 4, 5, 6. And then that extra electron is going to now join the oxygen over there. So that's what we have now for this one with 3 double bonds. So now let's go in to use the formal charges to figure out what's going on. So let's start here. The bromine formal charge here. To find formal charge, the equation is what electrons it can typically bring. So I guess N will be the number of electrons, and you subtract that from the number of electrons by itself. Okay, plus electrons shared over 2. That is a formula. I'm going to use that. So bromine brings 7 to the table, and right now in this, it has no electrons by itself, and it's sharing 8. So in this case here, bromine, that's 7 minus 4, is going to be 3. Alright, so it has a plus charge of 3 as a formal charge. Alright, and remember that we want to have a total of minus 1 here for each one, because BrO4, as they stated, is an ion with a negative charge, an anion. So that means these 4 oxygens, hopefully I have to make sure that they cancel out the plus 3 and even make sure that it goes beyond that. So the oxygen here, actually, this is for every oxygen there. It brings 6 to the table, but it actually, as you can see, already has 6 to itself, 6 electrons, and it's sharing 2 with the bromine each time. So 2 over 2, so each oxygen actually here is minus 1. As we discussed earlier, this already I can say is not as stable as they wanted. Look at how it's distributed to where bromine is literally being such a positive number and there's all negative numbers surrounding it. There has to be a way to rearrange it to where we actually get some more neutral pieces. And you will see that actually as we move on. So bromine in this case now has a double bond, meaning that now it still has 0 electrons by itself, but it's sharing, okay, instead of 8 from before, it's sharing 4, 6, 8, 10. Okay, so now bromine has a charge of 2. Okay, so now it's 2 plus. Alright, which means we're actually kind of getting closer, because with that, all we need now is 3 minus to get rid of this. And the oxygens, okay, down here, so like these 3, those ones would be still the same. 6 minus 7, whoops, 6 minus 6 plus 2 over 2. That would still be minus 1. So here would be minus 1, minus 1, minus 1. But the oxygen at the top, actually, as you notice, is actually going to be, it right now has only 4, and it's sharing 4. So this one actually equals 0. So this one, oxygen here is fine. And now we have 2 of them doing the same thing in the next, I guess, resonance structure over. We have 6 minus 4 plus 4 over 2, which is still 0. And that's happening to 2 of them now. And the bromine in this case, so I mean, the other 2 though is still going through the same thing of 6 plus 2 over 2, which is minus 1. So that means these 2 here, minus 1 and minus 1 there. And the bromine this time would be 7. Okay, minus 0 because it doesn't have any by itself still. But now it's actually sharing 12. And with that, it's only plus 1. So we're getting actually quite close. So you probably already guessed the hint that now with this bromine, that yes, it broke the octet rule, but it actually prefers this simply because of the fact that how do I do this? There we go. Because of we want to be able to make sure that, let's see here, as we go through, bromine in this case is 7 minus 0 plus 12 over 2. Okay, oops, not 12, sorry about that. Now if you counted it, it's 4, 8, 12, 14. And now we finally get bromine to be 0. Awesome. And there's only one oxygen, because the rest of the oxygens are still now with the double bonds, they're doing this. 4 over 2 equals 0. There's only one oxygen here, where it's 6 minus 6 plus 2 over 2, which equals to minus 1. Only one oxygen does that, which is right here. Okay, so when we talk about resonance structures, okay, the one that's going to be contributing the greatest to the resonance hybrid would be the last one. Why the one with 3 double bonds? The reason being is because that actually is the most stable one when it comes to the formal charges. There's no where it's like canceled out within the same molecule. It's done it in a way to everything else is neutral, and there's literally only one negative charge, which is actually what it translates to. Instead of it being to where I have like 5 positives and 6 negatives and I get 1 negative in total, what I've done effectively here is said I'm going to rearrange it so that everything else is satisfied, and that way I meet my minimum requirements to have that -1 charge. So this would be the most stable, okay? And as you can see here, they did draw that. So, and they did number it 1, 2, 3, and 4. So as I said, 4 would be the most stable. And as they go through, they explain the first structure. Exactly, they have a 3 plus and all these 1 minus 1s 4 times. And the second structure is a little bit less, and it keeps going. And then the fourth structure. So the lowest structure that gives the greatest contribution, as I mentioned, would be the fourth structure. Okay, so now let's go on to question 10. Okay, so we have